all problems that we are considering in physical chemistry and quantum theory can be represented either as differential operators and continuous wave functions or as matrices and vectors, right? And there is a notation named after person with first letter of the last name is D. Yes, yeah, thank you, Nate. Direct notation, which unifies this linear algebra vectors and matrices on one hand and functions and differential operators on another one. So in this notations, in this direct notation, the functions and vectors are represented by either Brian cat, right? Scalar product or matrix element is represented as sandwich with and operator as cat and bra, right? So they're all problems. Each problem which is originally formulated either as a in a vector space or as in space of functions can be done in its original representation, but in some cases there is an opportunity to do it directly in the Dirac's notation. So it is a hybrid between linear algebra and calculus, and I assure you that for many problems it is the shortest way. And even if you never play and never use it other than homework which is due next week, you may enjoy, because it is an interesting, less science, it's more math, but it is interesting way to process like vectors without writing long vectors. It's a very short string, and it beautiful and super quick way to compute things. So what do we keep in mind while practicing this stuff? The matrix elements which are in the, so if you look on matrix elements, they have their own specifics, and I'm repeating, but coming back to important things. If we are in the space of continuous functions and operators, then to take matrix element or expectation value, we take operator in between, wave function conjugated, wave function without conjugation, and integrate, right? If we are in the space of vectors, we do row vector, matrix, and then column vector. And if so, when we do it in the matrix operation from our symbolic representation, we remove the symbol of integration. And the Dirac notations summarizes that it's still operation of the same nature, and it doesn't include integration, and it is a little bit more closer to the matrix multiplication, but by use of this dyadic form, cat times bra, one avoids literal writing of big matrices and processing it element by element. So one can pick the only part that contribute at most, and use some, if there is a regularity and symmetry in matrix, one doesn't need to explicitly write each element. One can use equations and just common expression for elements. So this idea, this approach would help you to complete next homework really quick. And right now we will do very little exercise. I do not know how did I come to idea to assign the whole meeting, because it's a deal of 5 minutes. Maybe I'll speak more of next assignments. So what we are going to get is to re-obtain the energy of the ground state, of the lowest state of harmonic oscillator. But we already know, we already accepted that it will be 1/2 of the frequency times Planck constant, right? And this information is already hidden, is already encrypted in the way how Hamiltonian is, the energy operator is written. If you have it as a matrix, we can extract it from there. If you have it as an equation, we see that this 1/2 times h bar omega is there. So the problem that we are going to solve is trivial and evident, but we are going to process all steps in such way that when we see a problem a little bit more complicated, where the answer is not as evident, we can repeat similar steps and follow the logic. So what else we will meet? So we will meet the way how to represent matrix elements and expectation values. We will revisit an idea about identity matrix or identity operator. So if operator is added together with a number, we shouldn't panic because those are incompatible values. We should just multiply the number by identity operator, which is once over diagonal, right? And it can be identity operator can be inserted or removed to and from any matrix equation. So if you put it between matrix and vector or between two matrices that are multiplied, it changes nothing. And this trick also could be helpful at some stages. So the expectation values, identity operator, and what else? The snake that catches rabbit. So when we see summation and delta function in the same expression, they cancel each other. And then we change variable. So I'll probably speak a little bit about administrative things and then return, and all these components will be summarized towards finding ground energy, ground state energy of the oscillator. And I probably should share screen so that it will be easier to follow. So as you see from this little schedule, which is from previous years, we still have a couple of weeks to deal with harmonic oscillator. And coming meeting on Wednesday, we will just review the homework. We do this self-grading. On Friday, there will be your turn to speak here, and please submit on Thursday night. Okay, and then we will move towards dynamical aspects of oscillator. We will see how things are oscillated. The lucky one who selected the last question in the presentations will focus on excited state dynamics, and will partially do what we do in class. And the last month, whatever 3 weeks, we will focus primarily on the projects. So in a week from now, coming Monday, I will overview, and immediately, or maybe next meeting, we will make votes, and then it will be main focus. In the class time, I will split between stories about your research projects and remaining chapters of the physical chemistry, which we need to round up your education and get prepared to the next series. So we'll get through rotational motion, hydrogen atom, and then some chapters of interacting of light and matter. What should be a take-home message when you leave this class and enter PCHEM2? Do you have an idea? Is there anything valuable in this portion of the class series in this class that will be useful in the next one? Did you took? Oh, okay. So we have. So Adam completed 2 in front of 1, so he can teach us what is. I'll focus camera and you can just entertain us.
So, man, it is different from this course, but you revisit a lot of the same concepts, but you do a lot more computation with them. So it's important to that we, I guess, touch on the theory before we get into actually doing computations, and that's why PCHEM1 is kind of useful too.
So which practical equations can be borrowed to the next class?
So I think I remember doing Schrodinger stuff with that, and particle in a box is used, I think, quite a bit. But what I mainly remember doing is molecular partition functions and stuff kind of dealing with ideal gases and larger particles than just electrons.
Okay. Was there anything about harmonic oscillator? Useful?
Yes. Yeah, there was stuff about harmonic oscillator. I don't remember exactly. It was a while ago, but yeah.
Okay. Yeah. Thank you, Adam, for this little interview. And the practical thing for the next class. So Adam mentioned partition function, which means probability that a microstate happens, and it you all know it from naturally. It's like energy of a microstate divided by temperature, and then it goes into power of exponential Boltzmann factor, right? So right now we are studying a couple of simple systems, and we study their energies, right? These energies and how the energies depend on number of states will be plugged into partition function in the next class. So it is like minimalistic amount of information that you can borrow from here to there. So when we are speaking about wave functions, it's mostly for this class. When we are speaking about energies, it will be borrowed. So yeah, just a little comment because I just imagined myself on your place and was asking, like, why should I sit here and what should I take with? How long should I suffer of this class more? Okay. Oh, Joyce, the lucky one, because you will study the practical applications and look forward into the other parts of the class. Yeah, so I think I'm doing more than needed. So we some weeks we missed homeworks. Now we have a little higher density, but I hope it will be more relaxed towards the actual end of the class. But the calculational homework is due one Wednesday, another calculation next Wednesday, and on Monday, just summary of what you hear from the presentations. And if the questions look not clear, let me know. I can go over them privately by email or maybe during the Wednesday meeting. I thought they all are very simple and just literally what we do in the labs. But if some formulations of the questions look strange, let me know. I'd be happy to speak hours about them. Okay, I've got email. Well, of course, instructors always believe that class audience starts working on homework the day it is assigned, like a week or 2 weeks ahead. But wow, that's a dream. Okay, I'll yeah. It should be yeah, extra credit. Yeah, thank you for. Er- That's great. But sometimes the homework is being started at the very last night, which I was doing myself at the time, or maybe an hour before it is due. And I've got an email asking how to start number 3 and number 4. So number 3 just plug in and apply. So it's there is no challenge. You just will be 2 terms. One is multiplication, and another is derivative. And just see the differences. Those brackets symbolize in a simplified way creation and annihilation operator, because if you put all factors, it will be so boring and exhausting. I wouldn't tolerate it myself to solve. It's unnecessary. And by leaving out factors, you see just a major principle how the function is being changed upon this type of operators. For number 4, by now we do not I'll put it positively. We know certain amount of observables and operators, but not many, and we can play with this expression, maybe open brackets, and just inspect how it looks like and compare with differential forms of the operators that we already know, and we know not too many, like position, momentum, kinetic energy, potential energy. What else? We didn't discuss anything else, so you need to compare this 4 and the result of multiplying these 2 brackets. And of course, dimensionality factors are lifted, and maybe you identify some connections. So it's more logical thinking and writing a composition rather than doing mathematical exercise. Okay. So here is the one that is due in like 9 days, and you see it refers to this algebra of operators. And the stuff that we are going to do, that I was trying to review, and that we are going to do very briefly, will just help to get through it and get general thinking. Oh, too early. This is just options for projects, but I'll go over them next Monday. Okay, so here is where we stopped over last Friday, right? So the total energy operator, we used the functional form that originally was implemented to design the creation and annihilation operator, and now we plug them in. The product of creation and annihilation should give total energy, and after doing it, we've got this expression. So the dyadic form, which gives like minimalistic portion of operator, depending on what we put. So those states for either functions, eigenstates, or basis vectors, escalating factor. And this notation means that the operator will be non-zero only along main diagonal, right? When indices equal to each other. The factor here should be thought of as multiplied by identity matrix. And if you look on this in the matrix form, then it will be factors outside, zeros away from main diagonal, and then 1/2, 3/2, 5/2, 7/2, right? So maybe this is the only thing from harmonic oscillator that you need to the next course. But maybe more, but this is definitely will be used, right? Okay. So here should be number 30. And we will stop here. So we should confirm the information that is already known to us, that the energy of ground state is 1/2 of frequency and Planck constant. So in order to do so, we are going to take matrix element of Hamiltonian, right? Okay. This slide doesn't bring us to the answer. It is sort of self-evident expression, but I'd like to maybe go over it once again and check if everyone is happy about it. So if we just go element by element, right, it will give this ket times bra for the ground state, for the first state, for the second state, right? And when we see this dyadic ket times bra, it I really hate the next word, but a lot of authors call it projector because it projects one state into another. So it this bra meets some other ket and converts it into this ket, right? So it means if this operator meets something in ground state, it will reproduce it. And this element would correspond to 1 at the beginning of the main diagonal. Make sense? So the next expression means that if this operator meets system in the first state, it will convert it back into the first state. So it will correspond to the next one on the main diagonal. And we replace writing bigger matrix with just shorthand notation. Okay. Maybe with years, I will try to make this slide more entertaining and go over Wikipedia images and make a photograph of like bread and butter sandwich, because it is operator between two functions. But let's stay with word only. So if the goal is to find energy of a system when it is in the known state, and the state is ground state. I know it is a little silly game because we know the answer, but if you do not know the answer, what are the practical steps? So we take the function in which system resides with and without conjugation, put the operator of this observable in the middle and perform integration if we are in the differential representation with continuous functions and operators. If we are in the matrix representations, we need to have vector of the state, which will be 1 and all zeros, column and row, then we need the matrix of this operator, and we need to do row by matrix by column. And if we are in Dirac notation, we can like Hamiltonian, bra for ground, cat for ground. So the little exercise that we are going to do is equivalent either to integration or to just multiplying vector by matrix by vector. But I will try to avoid drawing matrices. So here, when we add together operator and a number, we can plug in the identity operator, right? So this first term with escalate, as index goes higher, the factor gets higher. This one is constant. And then we are multiplying this expression from left and right by this bra and cat vectors. Let me check, maybe I have a little better calligraphy. So factor goes outside, bra, cat, and this identity vector. What we are going to see when we will write it line by line, that we can open this summations and see that only terms where indices in the summation coincide with index of the state will give us non-zero contributions, and all other terms will drop, right? I just can't do it because that's basically it. Let's see, maybe there is a. So we may look that this term, this product of bra with ground state and cat with state under index will be non-zero only if k equals 0, right? And this pair will also be non-zero if k equals 0. So in some sense, it is one can put like delta k0 and delta k0 once again. Now I just need to slow myself down. In other problems, it could be different combinations, but we see a common situation that delta function appears together with summation, which means it parses only one term out of the sequence, and both summation and delta function will disappear. So after making this disappearance of delta function and summation, we will do two things. By setting here delta function, we already remove all wave functions, right? So there is no wave functions, no overlaps, there is only delta function. So they're already gone. And then we have summation, delta function, and this factor. This delta function and summation will be gone, and in here we will plug the value that will make delta function non-zero. We'll make 1. So we will plug in k equals 0. And then we will get h bar omega times 1/2. Yeah, one can put it this way. So to delta functions, and basically they are the same. They obey the same rules of interacting with summation, and then one gets an answer. So in which situations we may use this trick towards next homeworks? Well, anytime we need to find either expectation value or matrix element of an operator. And you saw it took, mostly speaking, the actual derivation is you see the answer through as soon as you formulate the problem. So the goal of this exercise was, I even feel sorry to waste your time because you knew the answer, but it is an encouragement to show that the next homework will be quite easy. So new notations may scare you a little bit, but in fact, it is simplification rather than complication. Let's see if I have anything else. So ground state of harmonic oscillator. Okay. Well, I can start very slowly talking about what will be the next, but basically we are done. If you have questions, stop me, and we should slowly wrap up and prepare to depart. I'll just start by words. We should prepare to depart. Adam made a glance towards the door. Someone is going to enter? Huh? Okay, so the little heads up what will be in the academic part in the lectures. So there will be long, maybe not very long, but I will give some motivation talk why we need the dynamics of harmonic oscillator. And basically, anytime your molecules are vibrating, you need dynamics rather than the static states. And quantized states, well, molecular vibrations are unique because they show both classical oscillation of like a center of a wave packet and quantum properties, depending on which experiment one is looking to. And to see the more classic like oscillation of the interatomic bond is really seen when we have FTIR, or just regular infrared spectra, when we tune infrared laser or any infrared source in resonance with molecular vibration and launch it to get bigger amplitude. And so I'm looking for about a week ahead. We will need to make a merger between your already deep and fundamental knowledges about quantum properties and skills of dealing with operators on one hand, and the fact that sometimes one needs to downgrade and look for simple oscillation. And we will need to identify whether it will be just oscillation of a center or there will be similar effects as you saw for free space when the dispersion, the width of the wave packet expands, whether it will expand or not. This is definitely a question beyond classical approach, and we will try to discuss how to launch these fast oscillations of the whole molecule, how the uncertainty distribution will change. And to answer these questions, we will look back on all tools and skills that we got by now. So this creation and annihilation operators, linear algebra will be used and I promise it will be a shortcut, much shorter than by any other methods. Okay, so I think we have general understanding how we progress towards the class right now.